common theme for engineers is to solve problems and solve important problems. And the problem I'm going to talk about today is this problem of lack of sanitation. So we're actually going to start this session with a little stretching exercise, and I'm going to ask everyone to stand up. Stretch your legs. Some of you just came from across campus. But so everyone stand up, and let's just imagine for a couple minutes that we are representing the world's population. And, we're doing this roughly. We're engineers. We're not doing things with like five-digit accuracy. But I'm going to ask the second row and the fourth row to remain standing, and everyone else can sit down. So let's do that. And so the second row, you guys over here, and fourth row to remain standing. Yeah, that's good enough. That's good enough. All right. That is roughly 2 out of 7. And those standing would be representing the population that has no access to decent sanitation. That means you have no decent toilet to go to. And now I'm going to ask the fourth row to sit down. And the lucky ones in the second row have no toilet at all. That means that when nature calls, you have to go out in the bushes, you practice open defecation. And that's the reality for about 1 billion people on this planet. Over 40% of the population in India is practicing open defecation. So now you can sit and relax. Everyone has nice toilets. And for the next 20 minutes, I'm going to tell you a little bit about the problem and about what we're doing, what kind of research we're doing in my lab and out in the field with graduate students, with undergraduate students, with researchers, and how we're trying to make a difference, how we're trying to solve this important problem. It's a very important problem in the sense that it has a huge environmental and health cost. As you can see on my slide there's over 2 billion cases of diarrheal diseases each year caused by this eternal cycle of pathogen release from fecal matter and being ingested. It has a big cost on children. Over 600,000 children die each year from diarrheal disease. And so these are pictures of what everyday life toilet might be for someone. And this actually was called a nice toilet, as you can see. It's a little dark, but essentially you see a channel here, and this is nothing just like a shed that shields you. And as you can imagine, this is where the waste goes, but in the back you have fields, and this is where you can imagine that the water will be irrigating the fields, and that's how we perpetuate this cycle. When you have access to some sanitation, well, it could be something like pit latrines. And these are pictures I took in South Africa in a middle-class neighborhood, and this is kind of an inner court with multiple houses, and this is their pit latrine. It's the outhouse, and you can see here they're actually cleaning the dishes. The toilet actually quite clean, but all the waste goes into a hole, and we're going to zoom in on this area here, which is where the waste is being received. And so what you do when the pit is full? Well, that's all the waste here, and there are people whose business is to go and take the waste out and dump it somewhere. Often the work is done manually with buckets, and they're carrying those through the houses into the street, into narrow streets, and putting it in big drums and moving them. And of course it spills, it stinks, it's filthy, it attracts flies, and really spreads pathogens which are then going to infect people. Where do they dump it? Well, the first place they find that they can get away with, and this is a river in the middle of a city where they would dump their content, and as you can imagine, there are kids playing in that water, there are people washing their clothing, all kinds of stuff. And this really is a dire situation. It's really intolerable. Really here, the foundation, the Gates Foundation, led by Bill and Melinda Gates, and you might know that Melinda is an alumni from Duke, has championed a program which is looking at this problem and trying to find solutions. It's called the Reinvent the Toilet program, and I'm lucky enough to have 2 grants from the foundation, and we're funding graduate student, undergraduate student researchers to find solutions to this problem. what they said is that it's not conceivable that for these 2 billion people, we have flush toilets the same way we have it in the United States or in developed countries, because there's just not enough water for having flush toilets for everyone. It consumes too much energy, and there's a need for too much infrastructure to have kind of the sewer and sanitation systems that we have in developed countries. So let's reinvent the toilet. Let's come up with the best engineers working to finding good solutions that work and eliminate this huge problem. What the sanitation methodology should do, it should remove the pathogens. It should also recover valuable resources. In your waste, there is energy. If you take your daily waste and you look at the energy that's embedded in that waste, it's enough to light a 25-watt bulb 24/7. So it may not look like a lot, but if you can engineer a treatment system that can use that energy to power the treatment, you don't have all the energy expenses. If you can recover the nitrogen in your waste, there's 7 grams of nitrogen per day. It's mostly in the urine. Now you may know that, or maybe you're going to learn it, that something between 1% and 2% of the world's energy is spent to capture nitrogen out of the air and turn it into fertilizer so we can grow stuff, we can ingest it and turn it back, and then it goes back to the atmosphere. 1% and 2% of the world's energy. So maybe we can recover those nutrients. Maybe we can recover clean water and do something with the clean water. We should be able to operate off the grid, very much like the cell phone revolution in less developed countries. They don't have phone lines anymore. They really rely on cell phones. There are actually more cell phones in India than there are toilets. And they should be affordable, but also they should provide and promote a decent sanitation business, meaning that there will be people having incentive to keep it, to operate, and that will make money, and that will enhance livelihood. So I'm going to now show you a couple projects, and we'll start with fairly low-tech systems that we invented in the lab. We did research and we're moving it into the field, and we called it the ADPL for Anaerobic Digester or Digestion Pasteurization Latrine. It's a self-contained system that uses the energy it produces to clean the waste and sanitize the waste. How does it work? Well, imagine that the waste from the toilet goes now into not a pit or into the open air, but into a vessel. And this is what we call an anaerobic digester. In there, under the action of microorganisms, they convert the waste to biogas. Biogas is pretty much what you have in your stove in your kitchen. It's, in the case of biogas, it's slightly diluted with CO2, but it has energy in there. And what we're doing is we are burning the biogas in a very efficient heater and heat exchanger system that we designed, and that allows us to take the effluent waste and bring it to temperatures where the pathogens are killed. So we're pasteurizing the effluent. So a few pictures here of how it looks like in the lab. This is our first prototype, designed out of plexiglass. We built it in-house. You can see some pipes for the waste in and out. It should be very simple. Remember that we're looking at populations that may be off the grid, so there's no moving parts. There's nothing sophisticated in there so that it can operate reliably. These are pictures of the digester as it is completed. This, by the way, is our synthetic poop. Always makes people laugh a lot, but it's a paste that has the same properties as fecal matter. It's a lot easier to work with that than with real waste in the lab. It's safer too. The biogas accumulates in the lid. This is a floating dome digester, just a little bit of jargon. Here you can see what the contents of the digester looks like. You can see some gas bubbles. This is what comes out. This is the treated effluent. It's by no means clean water. We're not trying to make clean water. We're trying to make something that is safe. And this has gone through our heating system, has been pasteurized, and so we don't have parasitic eggs or virus that are harmful. They've been killed over here. Or a few pictures here of our heat sterilization system. This is our first prototype that was built with very simple, a paint can and tomato soup can. But make no mistake here, we engineered this system. We engineered the system to the point that it would be Energy Star rated because we insulated extremely well. You can see some pipes here that are the exhaust. It's powered by the biogas, and the exhaust goes through the liquid. Actually, it's a scaled-down version of your gas heater that you have at your house. It works. We are testing it in the lab. You may be familiar with growing microorganisms on the plate. We're testing our heater and heat exchanger in the lab. We're feeding it some synthetic waste with bacteria, and you can see here we have 100 million in the inlet. Somewhere halfway through the system, we've killed a good portion of it, and what comes out is void of bacteria. So we're doing this kind of experiment to show it works and understand under which conditions it works and improve our understanding of the design and operation. We're moving these innovations to the field because this is where it's going to make a difference on the lives of people. And so last year, I had a graduate student spend the summer in Kenya. And essentially, here you can see a tinsmith, which is replicating our system. This is the heater that I showed you earlier. And we're building with local materials, we're building systems. And we built 3 such systems. The structure has elevated toilets. It has 3 toilets so that it gravity feeds into the digester. Here is a digester, and this is our heat exchanger, and this is the heater. And so we have 3 locations that we're testing. We're educating the people who are using it, and we're acquiring data to see how well it works in the field. And what we found is that the people are very interested in those systems. They're excited about the biogas. They're excited about the possibility of having liquid effluent as fertilizer. And we're testing the systems in multiple contexts because the problem is so huge that we need to understand the spectrum of conditions for which it might be applied. So we have a partnership with some folks in the Philippines. And then we're also in India, and this is a CAD drawing of a system that we have there. We have partnered with a company that designs high-tech toilets that clean themselves, and then we're providing the treatment at the tail end. And so you'll ask me, so, okay, where's the engineering in all that? What sort of things do we do with my students? So here are a few examples really quickly. This is the heat exchanger, and we are applying concepts of heat, momentum, and mass transfer to fully understand the flow of materials and the transfer of heat. And that allows us to optimize the design. And then we can size it, we can optimize the energy efficiency. These are heaters, and you can see this one has baffles in there, and that allows us to increase the pathogen killing in the heater. And as you can imagine, the system is very cheap. You know, this is a few $100s, and probably we got a street price for tourists in Kenya there. So this is a system in India with the self-cleaning toilets over there, and we're designing new digester. I have a picture in a minute showing you that how we configure the anaerobic digester allows us to increase the production of biogas and therefore also increase the waste treatment. We're also completely modeling the fate of the pathogen, because ultimately the main goal here is to kill all the pathogens. So we are doing comprehensive modeling to allow us to optimize the design. This is just an example of this digester with baffles, and we are conceiving post-treatments that will take the waste that I showed you earlier, that I said, you know, it's kind of a brew, and maybe in some cases you would want to have clear water so that you can flush the toilet, and that system, if successful, might do that. And we're following various steps, starting with computer simulations, injecting fundamentals of engineering, following then with lab experiments, and then we're taking those experiments, these results into the field. We're also using low-cost microcontrollers, little Arduino chips that cost close to nothing, to control our system. So we're injecting high-tech into low-tech systems, and that allows us to better operate those systems. As researchers, we're also able to acquire data and see how our units are doing in the field. We're having some fun too. Do you see the image on top? This is in India. I say, where's the engineering? We have to make our system monkey-proof in that particular case. They were able to get a hold of our duct tape. This is my graduate student working on this project. I got a funny email saying, hey, we got to put an enclosure around our system because the monkeys are tinkering with our system. That's not engineering, but we're trying having fun. In the last couple minutes, or 5 minutes, what I want to tell you is our second project. And this is a high-tech approach, maybe more science fiction, but actually it's not too far-fetched. And what this system is different. We call it an Omniprocessor for human waste. And the idea is that maybe in the urban poor, it would be very concentrated. You would need a treatment centralized and being able to take care of the waste. And this is what it's doing. And how is it doing? It's using supercritical water oxidation. I'll tell you in a minute what it is. The unit is to be housed in a 20-foot container that we have designed, and we're constructing it right now, and it's going to be operating in a couple months. And as you can see here, this is the vision where it would be a centralized treatment receiving the fecal waste, either through pipes or those transporters that we're dumping into the river, or motorized transporter, and we're turning the waste into clean water. So what you see here on the left side is our simulant waste, and this is a picture of the treated waste from our lab unit. And that water is clear. That water is odorless. We're not trying to make drinking water, but you could drink it. In fact, I've vowed that I will drink the water coming out of our unit just for shows, and I will put it on YouTube, so stay tuned. There are, of course, psychological barriers in turning poop into drinking water. So, some people would object, and I'm not going to comment on that. So, I'm thinking more like shower to flower. Maybe we can turn that into irrigation. We are going to produce a lot of hot water, and people can do laundry. There's value, and we are having part of our team also looking at how this integrates into the value chain. We're looking not just at engineering, but we're teaming up with professors in other schools within Duke to look at these aspects of the problem. So how does it work? Supercritical water is a pressure cooker on steroid. This is your pressure cooker, by the way. There's 100 degrees C in 1 atmosphere, slightly higher. And this actually is not to scale, so it doesn't fully convey the fact that you're increasing the pressure to 220 times the atmospheric pressure, and you're raising the temperature to something like 370 degrees C, and you enter this zone which is supercritical. It's not a gas, it's not a liquid. But what happens is that the organic waste in our waste stream, when it's brought into the supercritical regime, with air or oxygen, it oxidizes extremely rapidly, turns all the organics into CO2. And that's why we have this water coming out, which is really clean. This is just kind of a scale sketch to show you. This would be 1,000 people to scale. This is the fecal sludge that they would produce, about a 1.2 cubic meter that they would produce daily. Our 20-foot container unit can treat all that waste per day. So it'd be sufficient for a neighborhood or for a small village. Show you some pictures here. That's our container. Actually, if you walk from here to the LSRC, the Love Auditorium, you might see it. This is the inside, and you can see this giant coil here. This is a heat exchanger. A lot of the challenges is being able to recover all that heat. Remember that I told you one person, 25 watts. So 1,000 people that this unit can treat is, you would have roughly 25 kilowatts. And the challenge is to be able to treat the waste with those 25 kilowatts, or maybe recover some of that energy. And we know that we are going to recover a lot of that energy as heat and hot water. So where are the challenges? Well, heat and energy recovery. This is where we put our best engineering skills to make sure that we can recover that heat, the heat of the combustion. This is really cool, actually, to think that we're burning stuff in water in that supercritical water phase. There's some real challenges because at those high temperatures and high pressures in the presence of oxygen, metal corrodes, and we're using the latest alloys, and there's some real issues on process control. Also working in a lab, here, just with some pictures showing you that depending on how much excess oxygen that we put in the system, you see different degrees of waste conversion. And again, that water treated here, it might have a slight color, but it's really odorless and it's quite clean. So that's, in a very short time, kind of a highlight of these two projects and kind of draw the attention on a very important problem, which is the lack of sanitation. Tell you that we're working towards improving lives. We're working towards finding good solutions. But the problem is a very, very big, very important problem. It's very clear that the solution there's not a silver bullet. It's going to be a multiple of solutions. And it's probably going to have a portfolios of technologies depending on the geographic location and whether it's a rural or urban setting. And what makes it really interesting and also challenging is all the other factors that come into play. It's not just we need to come up with a better mousetrap. We need to make sure that it's integrated, that it's economical, and that people are going to adopt it. But personally, what I find is very rewarding because I know that down the road, this work will improve the lives of people who work in very dire situations. So that's my message to you. Thank you for your attention. And I think we have time for a few questions. Yeah, we have time. Yes?
You mentioned that these are only going to be widespread if they're locally incentivized by businesses of some sort. So how do you anticipate licensing or disseminating these in a way like that?
I didn't want to imply, incentivize with businesses. No, I think for technology to be adopted, it needs to have a good value chain. And what that means is that people should see that there's an interest and it should support healthy businesses. And so someone needs to be able to make money out of that. What we do know is that as poor as these people are, they're ready to pay for sanitation. They're ready to pay a significant fraction of their income to have a clean toilet. And if that, and that should be sufficient to drive the market and implementation of those technologies. Next question. Yes?
Do you envision at some point in the future getting locals involved with large scale production?
I'm sorry, I didn't hear.
I'm just thinking if you could have fast, just like Bill Gates himself has said about
Yes.
the problems of the world,
Yeah.
He's not patient.
Well, we can imagine different situations. We're in the business of innovation and bringing those innovations to the field and showing that they work. At some point, for these technologies to take, there needs to be businesses, just like I was saying earlier, that take these things and run. And it's very much the objective of the Gates Foundation is to, and they have a division that look at ready markets and are taking technologies and are trying to accelerate the technology transfer and implementation. I've seen, and Duke students for that are incredible. The entrepreneurs, and maybe in the room we have someone here who a few years down the road is going to open a business in sanitation for less developed countries. Think about, this is a business with 2 billion customers. Yes?
So this produces zero solids?
It produces some solids because what happens when you are treating the fecal sludge under supercritical conditions, the salts, most of the inorganic salts will precipitate. So what we have are carbonates, sulfates, phosphates, etc., that come out as solids. But typically we would have for the unit that we're showing, we will have a few kilograms a day, at most 5 kilograms a day. And those solids, we haven't yet fully explored whether they have any intrinsic value. We know that, it's not something that is going to fuel the economics of the whole process. It's not something that has a huge value, but we need to find an outlet for it. Sorry?
As a fertilizer base?
Yes, that's a possibility, yes. Yes?
Are there undergraduates involved in this research?
Yes, there are undergraduates involved in this research and actually in many of my research projects. And the way it works, I always tell students who want to be involved in research is that if you want to be involved in research, you can be involved in research. And the best way is to go knock on the door of a professor, having read his or her webpage and knowing that this is something that interests you. And if this, if the professor sees a genuine interest and has openings in the lab, you'll find an open door. There's some research that lends itself better than other for undergraduate research, and then some professors who are more open than others. I'm very open and always have undergraduates in my lab. And typically, I do one of two things. Either I associate them with a larger project. Here there's a lot of advanced engineering and design, so the undergrads would be more, having a wrench and tightening nuts and bolts. But I have other projects where you know, they actually are in the lab and doing experiments, and we publish together. Or maybe through the Pratt Fellows or other researcher or a student comes with their own idea or have something, and say, well, this is an idea, something you might be interested in, and then they have their own projects and find some space in my lab, a bench, and then off they go. Last chance, last question? Thank you very much. Enjoy the rest of your day.